Hola, this is the lecture video on section 3.1, which is the first video for our series on chapter 3 in geometry, which is called logic. Let's begin. So 3.1 is called logical reasoning. So we can start beginning to talk about shifting away from doing a little bit of computation right now. We kind of talk about how geometry is set up and basically kind of introducing us into proofs. And remember, we're not going to do any proofs in this chapter, but just kind of introducing. We'll talk about why we do this and the type of thinking we do to get there. Okay, so we'll start with this left column here. Let's begin. So we have inductive reasoning. This is a type of logical reasoning that we use in geometry. So inductive reasoning is the process of observing data, recognizing patterns, and making a generalization. This generalization is called a conjecture. I like to think of it kind of as like the scientific process, right? We do some experiments, we recognize some patterns, and from there we kind of try to conclude a general statement based on specific evidence that we found. Okay? These statements that we conclude are called conjectures. Basically, a conjecture is a guess. An educated guess, like you would think of hypothesis. Alright? And then these conjectures, since they're guesses, are not necessarily true. And the next part of our reasoning, called deductive reasoning, is where you take a conjecture and you use this process of deductive reasoning to prove a conjecture is true, and then it becomes what we call a theorem. So, but first we'll start with our inductive reasoning. We'll get to deductive reasoning in a second. Alright, so basically, like I said, inductive reasoning, we're taking data and patterns and observing them and making some generalization for like all statements, right? Not just specific numbers that we might see in math. Okay, let's look at some problems now. P1. 5 students attend a party and ate a variety of foods. Something caused some of them to become ill. Abby ate a hamburger, pasta salad, and coleslaw, and she became ill. Brian ate coleslaw and pasta salad, but not a hamburger. But he became ill. Colin ate only a hamburger, but he felt fine. Darby didn't eat anything and also felt fine. Fred ate a hamburger and pasta salad, but no coleslaw, and he became ill. Used inductive reasoning to make a conjecture about which food probably caused the illness. So first off, how about we look at who became ill and who didn't. Okay. Ill, not ill. So let's go read back through. Okay, we got Abby first. Hamburger, pasta salad, and coleslaw. She became ill, so she was sick. Brian, coleslaw and pasta salad, but not a hamburger. He also became ill, so Brian. Colin ate only a hamburger and felt fine, so he's not ill. Darby didn't eat anything, so she, of course, did become ill. And then Fred ate a hamburger and pasta salad and no coleslaw, and he became ill. Okay, we're going to look at now the 3 people who became ill. Abby, Brian, and Fred. Abby, Brian, and Fred. Abby ate a hamburger, pasta salad, and coleslaw. Brian ate coleslaw and pasta salad, but not a hamburger. So, hamburger's out. Hamburger didn't make him sick because Brian didn't have a hamburger, but Abby did, and they both got sick. So we can cross out hamburger. Now we're narrowing it down to pasta salad and coleslaw. So let's go back and look at Fred. Fred ate a hamburger, which we said was not, and the only thing else he ate is pasta salad. So I'm thinking probably pasta salad, but to make sure, let's check that Colin and Darby didn't eat pasta salad. Okay, Colin ate only a hamburger and felt fine. Darby didn't eat anything. So since all 3 of the people who got sick ate, the only thing they have in common is pasta salad. Alright. That means that we can probably make a conjecture that pasta salad caused the illness. This is an example of inductive reasoning. We're taking just specific examples and forming a conclusion from those specific examples. We don't necessarily know if the pasta salad causes illness, but we have enough based on our evidence, we can logically conclude that. So our next problem here wants us to use inductive reasoning to make logical conclusions, to make a conjecture, about the next two terms in each sequence. Explain in words the pattern you use to determine the terms. Alright, give me 1 second. We're going to start. Okay, so looking at our first sequence, we have A, then 4, then C, then 8, then E, then 12, then G, then 16. Okay, so what does this mean? So let's see if we can figure out a pattern here. Okay, so I noticed that what? Have a letter then number. Okay, so that's easy enough. Every even term will be a number, every odd term will be a letter. Okay, now notice that we skip a letter in between. So like B probably would have gone here. We go to A to C, so we skip in B. And from here we're just what? Adding 4. So right here we'll skip D. So basically we have every other letter. Every other term. Okay, and then numbers are multiples of 4. 4, then 8, then 12 is the next multiple of 4, then 16. So this is that. We skip H and we go to I. Then our next multiple 4, we have a number here, will be 20. So my words, the pattern I see is every other letter at every other term. And then the numbers that we have are multiples of 4. Okay. B. We got all numbers here. So let's see what we're doing. Okay. Well, let's see. How do I get from 3 to 9? I can add 6 or I can multiply by 3. Let's try multiply by 3. 9 times 3 is 27. Okay. 27 times 3 is 81. Okay, and then times 3. So basically all these are multiples of 3, right? So we can say multiples of 3. In order starting at 3, right? Another way you could have written this is 3 to the nth power, where n is the number term you have. 3 to the 1 is 3, 3 squared, 3 to the second power is 9, 3 to the third power 27, and so on and so on. So now we look at 243, multiply that by 3, we get that it is 729. Then we take this large number, multiply by 3 again, we get 2187. And it goes on forever like there. Okay. Now look at here. First off, I see 3 and 5. Add it to get between there, that's plus 5. Now what about this? 8 and 15. That's plus 7. Okay, I added by one odd number starting at 5. And the next odd number would be 7. I added that to my next. Let's see. I'm guessing this one's going to be 9. And you're right, this is 9. No, of course, okay, 11 plus 13. Okay, so I would add 15 to 48. That gives me 63. Then we add plus 17 to this one, and we get 80. So how about add consecutive, add next odd number starting at 5 to the previous term. Okay, so to get 8, we added 5. To get 15, we added the next odd number, which was 7. To get 24, we added the next odd number, which was 9, and so on and so on. Okay, this next sequence we have here is called the Fibonacci sequence. I actually like to see it a little bit better with the 0 in the front, but we'll see that. So, let's see if we can figure this one out. Okay, this one. Alright, this is called the Fibonacci sequence. So what if I did 0 plus 1? I get 1. How about 1 plus 1? You get 2. How about 1 plus 2? Oh, you get 3. 2 plus 3, you get 5. 5 plus 3, you get 8. 5 plus 8, you get 13. 13 plus 8, you get 21. Then 21 plus 13 is 34. So we say that each term is the sum of the two previous terms. And of course, this is called the Fibonacci sequence. I say of course, you probably don't know that. So Fibonacci sequence came up by this guy named, I think his name is Leonardo Fibonacci. And basically, he noticed this cool little sequence. And when you plot this as a logarithmic spiral, you get this really pretty spiral that shows up everywhere in nature, like in seashells and just so many different things. And it's also where we come up with the golden ratio, if you've heard of that. So it's a really cool sequence, really cool number theory sequence that we get that has a lot of cool, odd features in the real world that you wouldn't think would be from a simple sequence like this. Okay, cool. Alright, number 3. Anya is training for a 10K race. The table shows the distance she ran during the first 3 weeks of her training. The problem wants us to make a conjecture about the distance Anya will run during each practice on the 4th week. So first, let's remember we're doing inductive reasoning, so we're using stuff we know already that has been our evidence so far. So we're going to see how far she's run in the first 3 practices, okay? Her first week, she ran a half a mile. Second week, she ran 1 mile. And then the third week, she ran 2 miles. So basically, every week she's doubling her previous week's time, right? So, if our week 3 time is, we'll say, okay, so I can say that like she doubles, not her time, her distance, doubles previous distance each week. So if in week 3 she ran 2 miles, we're going to conjecture that she runs 4.0 miles in week 4. And how could you test your conjecture? So this isn't as hard as you think it is. Literally wait till she runs, wait till week 4 and measure how far she runs. So measure her distance in week 4. Number 4. Monique tosses a coin 3 times. She gets a head each time. Based on this pattern, she makes a conjecture that she will always get heads when she tosses the coin. Do you think her conjecture is correct? Why or why not? So here we're going to assume that she's tossing a very fair coin. Okay. So assuming she uses a fair coin, basically meaning that it's not weighted on one side for her to get heads every time. Okay. Assuming she uses a fair coin, then her conjecture isn't correct, is it? Okay, we think of flipping a coin, you have a 50% chance of getting either heads or tails. And I will say so 3 tries is not enough. To conclude this. Obviously, based on the 3 trials she's had, sure, you could conclude that, but just thinking in real life, and I might be using some sort of deductive reasoning here. However, she's not going to get, her conjecture isn't correct. But based on the evidence, it is valid for her to make this conclusion. However, in the grand scheme of things, knowing what we know, 3 tries, her coin's not always going to get heads. Okay? Alright, so that's inductive reasoning basically. Inductive reasoning is using specific evidence to form a conjecture or guess, and this guess might not always be true. Okay, deductive reasoning. In mathematics, there are certain methods and rules of argument that mathematicians use to convince someone that a conjecture is true, even for cases that extend beyond the observed data set. This is important. Cases that extend beyond the observed data set. Things that we have not observed, but we can try to make a form a conclusion based on statements that we already know are true. These rules are called the rules of logical reasoning or rules of deductive reasoning. Okay? An argument that follows such rules is called a proof. So basically, the rules I'm talking about are just statements that we have shown are true previously that we will use to form a conclusion on a new statement or conjecture that someone has made. A statement or conjecture that has been proven, okay? We've proven it to be true, that is established as true without a doubt. And we can do that in math. We can establish truth, logical truth without a doubt. This is called a theorem. Okay? So if you ever see theorem, the Pythagorean theorem, the different type of theorems that we have, these means that these are true because we have proven them to be true using statements, general statements that help support our claim. Okay? A proof transforms a conjecture into a theorem. So basically, in deductive reasoning, a conjecture becomes a theorem through a process called proof. Deductive reasoning uses true statements to logically show a conjecture or statement is true. Inductive reasoning makes a guess or conjecture based on specific evidence. Conjectures are not true until proven through deductive reasoning. So basically, inductive reasoning is kind of like a precursor to deductive reasoning. You observe some patterns, you make a guess or a conjecture, and then we start deductive reasoning to prove that this conjecture is true using statements that we know are true, like other theorems that we've previously proven that are true. Those are the type of statements that you'll use to show that a new conjecture turns out to be a theorem to be true. Okay. Number 5. Below is a definition from arithmetic. An integer has a remainder of 0 when it is divided by 2. So this is where we come in with definitions. Definitions are very much a part of our deductive reasoning. Definitions and theorems are what we use to show a new statement is true. So our definition from arithmetic says that an even integer is an integer that has a remainder of 0 when it is divided by 2. Okay? So, meaning every integer is divisible by 2, right? Every even integer. If you don't remember what an integer is a whole number, positive and negative whole numbers, and 0. Okay, that's what integers are. So it says calculate the sum of pairs of integers. Do this for at least 4 examples. Okay, so how about 4 plus 12? Or let's do 14. 4 plus 14. Okay. 18, also even. Okay. Now, how about some negative ones? Negative 12 plus 18. Okay, that's going to be 6. Also even. Okay, how about 22 plus 106. 2 plus 6 is 8, and then so 128. Again, even. Let's show one more. How about 2 negatives? Negative 24 plus negative 12 again. That'll give me, let's see, negative 36, which of course again is also even. So we're going to make a conjecture about this. So what can we say about the sum of 2 even numbers? Based on our evidence, we can make a conjecture that they are, that the sum of even numbers is even. So we'll say the sum of 2 even numbers is also even. Awesome. Number B. Now we'll kind of look at a geometric way to look at even numbers. Figures A, B, C, and D are puzzle pieces. Each figure represents an integer determined by its counting squares and the pieces in the figure. Using these figures, which of the figures can be used to model an even integer? Okay, remember when we have an integer, there are 2 rows in here, okay? So we want to find the ones that have a remainder of 0, meaning there's nothing left over when we have something done twice, okay? So if I count figure A, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, that's an even integer, so we'll say A. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So the top 2, A and B, are even. The bottom 2 are odd. What do we notice about the difference between the even and odd ones? The odd ones have this little jut sticking out, right? This means that it has a 1 left over more than something multiplied by 2, okay? These are basically even numbers right here, but an odd number is just 1 more than an even number always. That's why we have a little jut out right there. Okay, that's just a kind of a way for us to visualize even numbers geometrically. Okay, use the expressions 2p and 2m, where m and p are integers, to confirm the conjecture that the sum of 2 even integers is an even integer. Okay, let's talk about why 2p and 2m are even integers. Okay, any integer can be written in this form, right? Because if you divide any even number by 2, you're going to get another whole number, right? So p and m just represent those whole numbers that are multiplied by 2 to get our even numbers. Okay, so we want to show that, we want to confirm or prove that the sum of 2 even numbers is indeed an even integer. Okay, so sum means add, so we'll add 2p plus 2m. Okay, what do they have in common? They both have a 2 in common, so we can factor out this 2, basically the reverse distributive property. When I do that, I'm left with P and M on the inside of my parentheses, okay? This is an integer. So 2 times any integer gives me an even number. So we'll say 2. Some people is even because multiplied by 2. So the sum, we'll stop there. We'll state the conclusion right here. So it's to state the theorem for the sum of 2 even numbers, integers, okay? So we'll say the sum of any 2 even integers is also an even integer. And we've just proved this, so now this is a theorem. Awesome. So compare and contrast a theorem and a conjecture. Conjecture, this is a statement not proven to be true. And then a theorem is actually a conjecture that is proven true by deductive reasoning, or using deductive reasoning. So also, theorems are a product of deductive reasoning through proofs. Okay, so let's look at some stuff. I'm back. P7. The table below represents the function f of x equals 2x plus 5. Based on the table, Trent conjectures that the value of f of x is always positive. Is his conjecture true? And explain how you know. So look in here, you say it's always true, okay? But he's only tried 5x values and found that they're all positive. So if I'm gonna guess that it's false. It's the equation of a line. It's probably going to be negative at some point. Okay. All we need to show that it's not true is one example. We call this a counterexample. We'll talk about that next section more. But can we find an x value such that f of x is negative? How about we try x equals negative 3? So I notice that as we get bigger with our x's, it's getting more and more positive. So we'll try adding 1 to the left. Alright, so let's plug that in. F of negative 3 is going to be 2 times negative 3 plus 5. 2 times negative 3 is negative 6 plus 5, that's negative 1. So, when x is negative 3, f of x is equal to negative 1. So is f of x always positive? No. Trent is wrong. Okay. Good deal. The diagram shows the first three figures in a pattern. Each figure is made up of small triangles. How many triangles will be in the sixth figure of the pattern? Okay. So I got one triangle here. I got 1, 2, 3, 4. 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, these are all square numbers, aren't they? What's the next perfect square? 16. Let's guess that. See if we can figure this out for the fourth term. Try to draw it out. Okay. Alright, okay. Alright, let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So, the first figure was just that number squared, 1 squared. Okay. Second figure is the figure number 2. 2 squared gave me 4. Third figure was the figure number 3. 3 squared gave me 9. Figure number 4. 4 squared is 16. So 6 squared equals 36. That's what we're going to guess. Okay. Each number of small triangles is the figure number squared. Awesome. Okay, Todd knows that 3, 5, 7, 11, and 13 are prime numbers. Based on this evidence, he concludes that all prime numbers are odd. Is this an example of inductive or deductive reasoning? So basically what he's doing, he's using specific examples to form a conclusion. Okay? He just looked at those 5 numbers, those 5 prime numbers. And he said they're all 5 numbers. He's conjecturing this. This is inductive reasoning. Because he is using specific evidence to conclude. Alright? He noticed that just these numbers 3, 5, 7, 11, and 13 were both prime and they were odd. Okay? He's not correct. I'm going to tell you that, because if he had tried the first prime number we have, the number 2, he noticed that it's not correct. Okay, so that's the thing. With deductive reasoning, we prove something is true, the whole thing, right? If we don't prove it's true, we still have a conjecture, and we didn't finish our deductive reasoning. Okay? No, someone say no, because 2 is a prime number that is even. Prime numbers just mean any number that's divisible by only itself and the number 1. Okay, so 2 is only divisible by itself and 1, so of course it is prime, but it's also even. So not all prime numbers are even. There's one are odd. Not all prime numbers are odd. There's one even prime number, and it's number 2. Number 12. Oh, no. Number 10. Shayla knows that all rectangles have 4 right angles. This is a true statement that is known before she went in there. She's not looking at 7 different rectangles and noticing that they all have 4 right angles. She knows this is a true statement. She also knows that figure ABCD is a rectangle. That's given to her, also a true statement. Okay? She concludes together that figure ABCD has 4 right angles. And she's concluding this based on these 2 statements she has right here. She's not looking at 5 different rectangles and noticing that they have right angles and everything. This is an example of deductive or inductive reasoning. This is deductive reasoning. She is using true statements only to make her conclusion. She actually uses something we call the transitive property that we'll talk about later. So, basically what she said was rectangles, 4 right angles. Basically, rectangle equals 4 right angles. Okay? Also that ABCD is a rectangle. Okay? Since rectangles have 4 right angles and ABCD is a rectangle, from there we can say that those 2 are equal. Or those 2 are the same. So ABCD, 4 right angles. which is what her statement is, and yes, that's true. This is using something we call the transitive property. If two things equal the same thing or have the same thing, then you conclude that for each other as well. Right. So this is yes based on our deductive reasoning. Number 11, based solely on the pattern in this table, so he doesn't know anything else, he just has this table. Andre states that the number of sides of a polygon is equal to the number of its angles. Okay? Is Andre's statement a conjecture or a theorem? Explain. So what he is doing, he doesn't know that this is true. The size of number of sides in a polygon is equal to the number of its angles. However, all he knows is what he has in front of him in this table. Okay? He's using specific evidence of polygons. He's not using statements that are true about all polygons. He's using them for specific types of polygons. He sees that these three polygons, his statement is true. Okay, so since he's just basing it off this, since he is basing his statement solely on the data in the table, his statement is a conjecture because he's using inductive reasoning, and inductive reasoning only creates conjectures, right? Because these conjectures are not proven for all possible shapes. Okay. If he wanted to show this with a theorem and show it's true for any type of shape, he'd have to use some type of logically true statements, logically true general statements to support his conjecture and make it a theorem. Okay, number 12. Hairs found at a crime scene have many similar characteristics to those of the suspect. Based on the evidence, an investigator concludes that the suspect was at the crime scene. Is this an example of inductive or deductive reasoning? So we look at the crime scene, the investigator. They look similar to the hairs that they find. Look pretty similar to what the hairs of the person are. Right? So basically, he's looking at the hairs of a person using this specific evidence to conclude that the hairs are at the crime scene were the person's. Okay, he doesn't know this for sure. He doesn't know that the person was at the crime scene. Okay, he's making a guess with a certain degree of accuracy that based on this hair evidence. Okay, this is inductive reasoning. Most things we do in with police and investigators like that are what we call inductive reasoning, unless you have concrete proof that this is it. And a lot of science stuff is very much inductive reasoning statements, because the statement was concluded based on specific evidence and we don't know that it's 100% true. That's why we have trials, basically, right? Because this stuff, if you don't present your evidence enough, you don't present this with airtight logical reasoning, then stuff like this can come out and you can put it in a Samantha way or something like that. Okay? And that's our video for lesson 3.1, logical reasoning. This stuff might be a little bit confusing. It's okay if I'm not going to really push pretty hard for you to figure out the difference between inductive and deductive reasoning. However, I do want us to get used to the different ways of thought that we might go about as we move into proofs. Right? Deductive reasoning is definitely more the important part as what we do when we're doing proofs. Okay, so it's just kind of getting you an introduction to how to think. You do have homework, 12 questions. Please email me if you have any questions. Thanks, guys.